Welcome to the 60th Theoretical Physics Colloquium by Professor Francesco Becattini from the University of Florence, and he is also an associate member of INFN. He got his PhD in 1995 from the University of Florence, and he did his work in experimental physics, as far as I know, working at CERN. Afterwards, he had a postdoctoral position at INFN from 96 to 98, and then a brief postdoc at the University of Florence before he got a faculty position at the University of Florence in 1999. He is a member of the International Editorial Council of Acta Physica Polonica B and an elected member of Academia Europaea. His research interests include relativistic heavy ion collisions, quantum statistical physics, strangeness production in heavy ion physics, relativistic hydrodynamics, role of spin and polarization of relativistic hydrodynamics, many other things. And today he will be talking about new developments in spin physics in relativistic heavy ion collisions. And with that, I'll give the microphone to Francesco.
So thank you very much. Can you hear me well? Yeah, okay.
Yes.
So I would like first to thank the Igor for this opportunity to give this colloquium. And as you see from the title, this is about the recent work in spin physics in relativistic heavy ion collisions, which was done in collaboration with Matteo Buzzegoli, Andrea Palermo, Gabriele Ingirame, and Yuri Karpenko from the University of Prague. This is about something that we did over the last, say, I would say 10 months over the pandemic silence time. And so this is, I'm very grateful for this opportunity because this is one of the, one of the mean to spread out, knowledge about people's work. So the outline of my talk is as follows. So I will introduce the subject as there are supposedly graduate students and PhD students in the audience. Then I will talk about the brief history of spin in relativistic heavy ion physics, focusing on the theory. And I will then move to the new part where a new term which has been found independently by our collaboration and the Chinese group led by Yi Yin. So the spin, it is a term relating the spin to the shear tensor at local equilibrium. And then I will show the applications which have been followed from very quickly in the phenomenology of heavy ion collisions. Then, if time allows, I will speak about possible new application of spin physics in relativistic heavy ion collisions, namely a possible way to use it as a measurement of the local parity violation in QCD, similar to Carl magnetic effect. So that brief introduction, I think that most of the people in the audience know what the relativistic nuclear collisions are. So the idea is to collide two nuclei at very high energy. And this is the energy range where the collisions are taking place at the highest energy in this time. So in the United States, relativistic heavy ion collider between 7 and 200 GeV per nucleon, and in Europe at LHC at CERN between 2.76 and 5.5 TeV. The goal of these collisions is to produce and to study the new phases of the quantum chromodynamics at finite temperature and biochemical potential. So to study the QCD matter in extreme conditions and to form the so-called Quark Gluon Plasma. So the phase where quark and gluons deconfine from hadrons and they can move, say, in a something which can be properly called matter. So a larger system which is much larger than a hadron. QGP itself, let me just summarize this, because QGP itself is an extraordinary fluid. It is the hottest ever made. So the temperature which is estimated to be achieved in these collisions is of the order of 5 billion degree kelvins. And on the other hand, because of this so large temperature, it is the tiniest ever made. So this can, of course, is a consequence. So we cannot produce such a large amount of energy, of the energy density, if the system is not small. So it's only 10 Fermi cross. And interestingly, that this is not so popular. It is this fluid, which is described hydrodynamically, has the largest initial pressure ever made in a fluid, the largest energy density, and the largest initial acceleration, which is estimated to be of the order of 10 to the 30 times the gravity acceleration on Earth. Just to compare with something which is known as astronomically high, the surface gravity of a black hole is 18 degrees of 18 degree of degrees of magnitude lower. So it is much, much higher than the surface gravity on the black hole at the event horizon. And which is very popular, it is the lowest, it is so-called the most perfect fluid, except the Bose-Einstein condensate. It is the lowest viscosity, it is the lowest, say, the most perfect fluid because it has the lowest viscosity or entropy density ratio ever observed, which is shown in this very well-known plot showing that the ratio eta over S is a minimum for the Quark Gluon plasma compared to other known substances. This is very important because the ratio eta over S is a proxy of the ratio between the mean free path and the thermal wavelength. So in other words, this fluid is such that the ratio between lambda, the mean free path, is comparable or even smaller than the thermal wavelength, which means that it cannot be described in terms of colliding particles which are free from most of their time. So these are really a strongly interacting system because you cannot even conceive it in terms of colliding or in kinetic terms of colliding particles, after long time of free propagation. Okay, one of the important feature of heavy ion collisions is that in peripheral collisions, so if the impact parameter of the nuclei is finite, they produce a system which has a large initial angular momentum. So if you collide the two nuclei, they are collided with finite impact parameter. What happens is if the plasma is formed, it must have some large initial angular momentum, F. And if the system has enough time, what can happen is can distribute this angular momentum to the various degrees of freedom of the particles. And among the degrees of freedom of the particles, you have orbital degrees of freedom, so the motion of the particle itself, and the polarization states, if they have. And this idea was put forward in 2005 by Liang and Wang, and they estimated the polarization at quark level by using a, say, QCD-inspired model a kinetic model by using, a calculation based on the spin-orbit coupling of the particles. Then it was, amended in the 2008 in this paper by Fulvio Piccini and myself, where we assumed that, like the momentum degrees of freedom, also the spin degrees of freedom could come to the local equilibrium. So we used the idea of achieving the idea of the fluid, namely that you have the formation of local thermodynamic equilibrium, and by means of a statistical mechanics-based calculation, you could calculate what is the amount of the polarization of particles. The global polarization, which is expected in this calculation and in the previous as well, is that particles get polarized along the direction of the angular momentum, which is orthogonal to the reaction plane of the nuclei. In this calculation, I'm sorry for this symbol, it should be proportional, so that this PDF transformation had some problem. So in this calculation showed that at local equilibrium, the spin should be proportional, so the amount of polarization should be proportional to the vorticity, loosely speaking, more precisely the thermal vorticity that I will be talking about a little later. How to observe this polarization? Well, this polarization can be observed by measuring which polarization which should be for all particles. So all particles should be polarized as coming out from the hadronization of the plasma. Can be observed specifically for the lambda hyperon, because lambda hyperon decays weakly And this means that because of the parity violation, by measuring the momentum distribution of the proton in the lambda race frame, one can infer the polarization of the lambda itself. And this is shown by this formula, which is quoted here. So that distribution of the proton in the rest frame of the lambda is proportional to a quantity which involves the polarization vector of the lambda in its rest frame times a coefficient which is related to the fact that the parity, the weak decay breaks parity conservation. This coefficient has recently been updated by the particle data group. So has been 0.642 plus minus, say, I think an error on the third digit for a very long time. But in 2020, a new measurement raised it to 0.75. So this is remarkable. One of the few, say, big changes of PDG as time goes by. Now, this was the technique which was used by the STAR experiment in 2017, and it worked. So this is the they got the first positive evidence of the global polarization of lambda hyperons by measuring the proton momentum distribution in the rest frame, and it turned out that both lambda and anti-lambda are polarized to some percent with a polarization which decreases as a function of the energy, and it was found, say, the evidence was found especially in the range between the 7 and 60 GeV, so in the beam energy scan range. And this was, the first evidence of a global polarization, and it was acknowledged by the Nature magazine with a cover, the dedicated cover, with the title Subatomic Spheres, just because of the link between the polarization and the vorticity, which was suggested by the paper that I mentioned. The fact that lambda and anti-lambda have the same sign of polarization definitely favors the statistical hydrodynamic interpretation compared to, for instance, some mean field interpretation. Because the coupling, so if it was a mean field, the argument is very simple. The coupling should be generally charge conjugation odd, and this would result, like for instance, for the electromagnetic field, in a different sign for the particle and antiparticle. But in this case, you don't see it. So this really speaks in favor of a statistical driven phenomenon. The agreement between the hydrodynamic predictions and the data, as far as the global polarization is concerned, is really remarkable. In fact, you can see this is, I mean, I report a calculation by Yuri Karpenko and myself in 2017, where we calculated this as a function of the energy by using this formula, which relates the spin polarization vector with thermal vorticity. Then I will explain, in a few slides what this is. And this is a comparison with the original data published by the STAR collaboration. So that the agreement between the calculation and the data was quite remarkable. We also took into account this correction due to the decays, which seems not to change much the amount of polarization calculated for the primary lambdas. So because many lambdas come from decays of sigma naught and sigma star. This is an updated comparison up to 2020. You can see that this agrees not just with the hydrodynamic calculation that I showed, but also with many other calculations. Many other calculations based on different models of the collision, AMPT, URQMD, S3 fluid dynamics, chirokinetic calculation, and so on and so forth. And what should be pointed out, though, is the fact that all these calculations agree with the data, but all of them use the same formula. So the formula that I reported here. So they differ in the calculation of the thermal vorticity of the field, in other words, of the velocity and the temperature field. So once they find this with some, assumptions about the initial conditions and the model of interaction and so on, they produce this map, and applying this formula, they find this result. So different model of collisions, same formula for polarization. Now, what happened later is that this nice agreement did not extend to the so-called local polarization. So the polarization of the hyperon as a function of the momentum of the particle itself. So because the experiment were able to measure not just the global polarization, the integrated overall the moment of the hyperons, but also specifically in different, say, differentially as a function of momentum, of rapidity, and especially important as a function of azimuthal angle, the azimuthal angle of the transverse plane. And this is very important because it showed that there is a really an important major discrepancy between the prediction of the hydrodynamic model and the data. You can see here, this is the measurement by star collaboration as a function of the azimuthal angle with respect to the reaction plane. And you see that it predicts that the polarization along the angular momentum should decrease as the lambda, as the momentum of the lambda is rotated in this plane. Okay, whereas the model predicts the opposite behavior. So an increase from 0 at the or negative at the in the reaction plane to through positive at pi half. This is also shown in this color contour plot. So blue is negative, red is positive. So this shows that this component of the polarization is negative, or say almost zero if you integrate over the this range of d, and then becomes positive at 90 degrees. Similarly, the longitudinal component, so the component of the spin vector along the beam, is has a different behavior compared to the data. So it has it shows an oscillation. This was predicted by the hydrodynamic model. It has a sort of say V2-like or elliptic flow-like oscillations in the azimuthal plane, but the sign of this oscillation is the opposite as observed in the data. So this is the prediction and this is the measurement. You can see they are different. And this difference was found by other calculations. So not just say, it was not just us, it was say many groups tried to calculate the longitudinal polarization. They found in most cases, I would say, unless it's a special say assumptions were put in, they found basically the same result. It was also found that this has nothing to do with the decays. So once you include the decays into the of sigma naught and sigma star into the calculation, that very little is changed. So that as in the global polarization, the effect of decay seems not to be seems to have very little numerical impact. So how to solve the problem then? So this is the so-called called the sign, the polarization sign puzzle. How to solve the problem? There were many, of course, once you have a problem, a disagreement, that you have many proposals, and there were many indeed. And then I'm sorry that I could not list all of them, because that many people were involved in this calculation, and there was quite a large range of proposals, going from say an effect of the final hadronic interaction rescattering. So this was attributed to the fact that hadrons may rescatter, of course, after the hadronization. They could this can change the polarization to some extent, or it may be an effect of a term which was forgotten in the formula. So the effect of dissipative corrections. This has been investigated by these people and others, or it in a more, say, this is I'm going down in say in the going down means that the proposal becomes more and more radical. So another say somehow radical approach was that, okay, no, this is a problem that local thermodynamic equilibrium, so we cannot really correct with these dissipative corrections. We have to take a more radical approach and calculate the polarization by using a kinetic theory, because maybe spin is not strongly interacting with this spin degrees of freedom, does not feature the same strong interaction as, for instance, for the momentum degrees of freedom. So maybe kinetic theory is the right approach. And then, of course, there have been a lot of work and very interesting developments in the kinetic theorem of massless and massive fermions. So earlier I mentioned some people who were involved in this effort. And finally, one very radical approach is that, okay, that maybe there is a significance. So this is one of the instances where the spin tensor is significant. So there is an ambiguity in quantum field theory as to the definition of the stress energy tensor and the spin tensor. So maybe this is this disagreement is the symptom that we have to give the spin tensor a physical significance, and therefore we have to revise, say, our approach and our formula, and perhaps this thermal vorticity is not the tensor which drives the polarization, and we have to include a specific tensor which become a new hydrodynamic variable. So this was the idea. Okay, now I'm going to our recent work, and then before I get into the detail, I have to make a sort of short summary of the theory of how to calculate the polarization in relativistic fluid. So how to produce a prediction for the spin in relativistic heavy ion physics, if you believe that the Quark Gluon plasma is a fluid. Now, the main tool to calculate, so this is very interesting because it requires a quantum, at least this is my strong opinion, it requires a quantum approach from the very beginning, because spin is inherently a quantum object. Therefore, it should be tackled quantum-wise from the very beginning. So the main tool to calculate the spin polarization vector is the covariant Wigner function of the free Dirac field, in this case, that which is defined as the Fourier transform of the two-point function of the fermion field with 4 degrees of freedom. So A and B are indices, spinorial indices running from 1 to 4. Now, this angular bracket stands for the trace over some statistical operator. So it's a mean value. And by using the Wigner function, it is possible to show that you can calculate the one particle spin density matrix for a spin 1/2 particle, which is calculated as an integral over some hypersurface of a combination of spinors and the Wigner function. So this is the importance of the covariant Wigner function, because it allows to express this as an integral over some space-time region. And from that, you can derive the expression of the mean spin vector in 3 equivalent forms, involving traces over the spinorial degrees of freedom of the Wigner function multiplied by either the generator sigma beta gamma, they're the generator of the Lorentz transformation of the Dirac field, or gamma mu gamma 5, which is the axial current density, or the canonical spin tensor. So there are different forms, but they are all equivalent. Can be shown by using, say, using known relations involving the gamma matrices and the spinors. Now, what the crucial ingredient in this calculation of the Wigner function is the density operator. The density operator for a fluid which is believed to achieve local thermodynamic equilibrium can be calculated by maximizing the entropy with some constraints on the densities. So instead of constraining the total energy and total momentum, one constrains the energy momentum densities. This has been found and proposed many, many years ago by Zubarev and his group and the De Groot group in Amsterdam. And this covariant it can be written in a general covariant form, which is reported here. So the integral over some hypersurface of the combination of the stress energy tensor and the 4 temperature vector 1 over TU, which becomes really a very important, even primary quantity in this game, and the term which involves possibly a conserved current, with the ratio between zeta is the ratio between chemical potential and temperature. Now, this is the local thermodynamic equilibrium density operator. But the local thermodynamic equilibrium density operator in general is dependent on time. So it depends, in relativistic language, it depends on which hypersurface is chosen. Therefore, in order to make it time independent, in the Zubarev theory, that the idea is the following: if a fluid achieves the local thermodynamic equilibrium at some time, namely at some hypersurface, the actual density operator to be used in order to make calculations of everything is the density operator calculated at hypersurface where this local thermodynamic equilibrium is originally achieved. In other words, for the Quark Gluon plasma, this means the usual, or the hyperbola in the Bjorken model, where we believe that we suppose that local equilibrium is achieved and the plasma becomes a plasma. Now, by using the Gauss theorem, so now now in the physical Quark Gluon plasma we have two remarkable hypersurfaces. The first is the equilibration hypersurface that is in the Bjorken model believed to be this hyperbola or hyperboloid. Then we have the freeze-out hypersurface where the plasma ceases to exist. Now, by using the Gauss theorem, what we can do, we can recast this integral as the sum of an integral over the final hypersurface, sigma tau, which is then chosen to be the sigma freeze-out, plus the integral of the gradient of this, the gradient of the integrand over the region, which is encompassed by the two hypersurfaces, namely the QGP itself. Now, this theory has a big plus because it allows the Zubarev approach. It allows to nicely separate what is dissipative, from what is non-dissipative. Everything which is calculated with the first term is non-dissipative. It is a local equilibrium. Everything which involves this term is dissipative. So there is no ambiguity. And then, incidentally, also, this formula shows when global thermodynamic equilibrium is achieved. Global thermodynamic equilibrium is achieved when this term vanishes or when this becomes independent of time. These statements are completely equivalent. And if you then study when this can happen, and then you find that this, in order to vanish, in order to make this integrand vanishing, then there are two sufficient conditions. The first is that beta, so the fourth temperature vector, is a killing vector and fulfills this equation in Minkowski spacetime, and the ratio between chemical potential and temperature vanishes. In Minkowski spacetime, this has a known solution which is linear in X. So this beta mu equal B mu plus thermal, so because omega mu nu X nu. So it is where B and omega are constant. And in this case, once this solution is plugged in, what you can find is the density operator, a general global equilibrium, becomes a linear combination of the generators of the Poincare group, so involving energy, momenta, and angular momentum and boost, multiplied by suitable constants. But we do not have global thermodynamic equilibrium in the Quark Gluon plasma. So what we can do is that what we should do, we can calculate the whole thing, and we cannot do that in general. I mean, because it is very difficult. And so what we can what we can do as a first approximation is to retain the local thermodynamic equilibrium term and neglect about dissipation. This is equivalent to saying that I'm using a perfect fluid model. Now, this means approximating the density operator with this local equilibrium form. So, but just retaining the first term in this expression, just retain this. Now we have to calculate this integral. If you want to calculate something at the freeze out, then you have to calculate this integral of which is an operatorial integral at the freeze out, which is also very difficult. Now, the mean value, but we do not want to calculate rho itself. What we're interested in are the mean values, and specifically for the spin, we're interested in the mean values of the Wigner function. The mean values of the Wigner function is given then by an expression involving the operator and this and the density operator. Now we believe that we are dealing with a hydrodynamic system. What does it mean? It means that we believe we have a separation of scales, meaning that the scale over which the hydrodynamic quantities vary significantly should be larger than the microscopic scales. So the mean free path, we believe that the mean free path or the interaction scale, QCD interaction scale, is much, much smaller than the scale over which, for instance, the temperature varies by 10%, or the velocity varies by 10%. Under this assumption, what we can do in order to derive a good approximation of the mean value of the Wigner function is to expand the beta field from the point where x is to be calculated. And so write beta equal beta, which is a function of the integration variable, beta nu x plus derivatives in x, y minus x, lambda, and so on and so forth. And if you do this, and then you replace the Taylor expansion in here by truncating at some point, what you do is that if you truncate a leading order, what you get is simply beta nu x times this integral, which is but the forward momentum, because T mu nu is zero divergence. Therefore, this is generator of the translations in the Poincaré group. So the forward momentum operator. This is correspond to the so-called ideal or perfect fluid approximation. So if you replace this W with T and then say this, thereby you would obtain the so-called perfect fluid expression of the stress energy tensor. But we can go on. We can include the first order derivatives. And if you include the first order derivatives, it is very interesting to separate the symmetric from the antisymmetric part. And then you have that a good approximation to calculate this Wx is to write beta mu p mu plus the antisymmetric derivative, which couples to an operator which is just the angular momentum boost operators of the quantum field theory. And then you have also symmetric part, which multiplies this q mu nu x, which is the symmetric combination of x and t, and which is, unlike j mu nu, has no zero divergence because it is not a conserved operator. So it is well known that this j mu nu x is conserved. It is a generator is a proper generator of transformations, and the integrand vanishes. The divergence of the integrand vanishes. The divergence of this integral does not vanish instead. So we can write something like this in a more compact way, where you have the antisymmetric part, which is dubbed as thermal vorticity, and also we have a symmetric part, which is dubbed as, by analogy, as thermal shear. Now, both these quantities are adimensional. This is very important in natural units. Therefore, one can, once you have something which is adimensional, you can say, okay, if it is small, then I can expand. And this is what, in fact, what we can do. In fact, if they are small, we can expand the exponential. So this is, we have the exponential of the sum of several terms. If these are supposedly small, what we can do, we can expand in the linear response theory, taking into account that they are operators, therefore they do not commute. You cannot make a normal expansion of the exponential. You have to do it with the cuboid identity. This is well known as in quantum statistical mechanics. And what you are left are, so by separating two terms, the main term is assumed to be the one involving Hamiltonian and momentum, so minus beta mu p mu, and the small term is B, is the one which involves the thermal shear and thermal vorticity. Therefore, once you have plugged the expansion into the mean value of the Wigner function, what we can obtain is a good approximation at linear order in omega xi of the Wigner function. It involves the calculation of two correlators, and this is most of the job. So how to calculate these correlators and to find out the quantitative, say, final formula. Now, the mean spin vector and leading order in thermal vorticity, the formula that I have mentioned at the beginning of this talk, was obtained by neglecting this term. So the first time we did that, this was back in 2013, if I remember. Then I don't remember exactly, but I said I probably assumed that this did not give any contribution because in the mean spin vector, that this Levi-Civita tensor appears. Okay, So that I assume, okay, I have a symmetric part, and then okay, this is just vanished by this contraction with the Levi-Civita. So it was in a sense neglected by prejudice. So the calculation of the formula that we see here has been obtained by removing this by hand, just by prejudice, I would say, and retaining just this term. On the other hand, there was also another hint that a global equilibrium, this vanishes. Therefore, I thought this is not very important compared to this, compared to the coupling between the angular momentum and the vorticity. So if you retain this term, what you get eventually is this formula at linear order. So which has been obtained by rederived with other approaches, even by several people. So that's been confirmed. But this formula here, where you have the derivative, so the antisymmetric derivative of the beta vector, because you have epsilon nu rho here and then nu rho here. And F is the Fermi-Dirac distribution function in phase space at given for temperature. Okay, but surprise, by reanalyzing this with care, we found out that no, that term gives this term here can give a contribution. It can give a contribution. We found out that there is a special contraction between Levi-Civita and momenta of the particle and the thermal shear tensor, which does not vanish. This same formula was obtained a few days earlier, posted a few days earlier by Shuao Liu and Yi Yin with a different method. It's not precisely the same. Let me say this. There is a difference which is concerned with this vector here. So, and this is still under examination by both groups. Now, the dependence on the specific vector, let me say, it depends on a specific vector. What is this vector? This vector is the time vector in the QGP frame. So in the frame where the QGP is at rest. The dependence of the specific vector is not, can appear as a okay, this is wrong because it breaks covariance. It is not, because it arises from the correlator of this operator Q and W. But Q is not a tensor operator, in fact, unlike J, because it does depend on the hypersurface. Let me explain this. This is a general quantum field theory fact. If you have the integral of, if you have an integral of something over a hypersurface, in order for this to be independent of the hypersurface, the divergence should be 0. Okay. In quantum theory, in group theory terms, if this is the case, that means that under a Lorentz transformation of J mu nu x as operator, this transforms into the nice way, so like a proper tensor. But if you have something which has not divergence 0, then this is not a good tensor operator, because under a Lorentz transformation, which transforms the domain of integration, it also changes the tensor. Therefore, you have that the equality is not fulfilled. So you have that lambda q mu nu, lambda minus 1 is different from this. And therefore, when you calculate the correlation of something with this tensor here, you expect a specific dependence of the hypersurface, because this object should have another, say, symbol here in the subscript, which is sigma. So it depends on the hypersurface. And this T is somehow summarizes the dependence on the hypersurface. It's say, in a sense, it's the average normal vector to the hypersurface of result in the QGP frame. Now, what is this new term? This has been found, as I told you, by 2 different groups, and it involves a coupling. So if you decompose everything, it involves a coupling between the spin and all of these tensors, including the shear, the properly called shear tensor, the expansion scalar, a symmetric combination of acceleration and temperature, and the gradient of temperature. All of these terms, so the third, the fourth, and the fifth, are they vanish in the infinity limit, so they do not have a non-relativistic limit. On the other hand, these 2 terms, they do have they do have a non-relativistic limit, which is very interesting. It is the vector product of the velocity of the particle times the gradient of temperature with some integration. There is an equal contribution in the non-relativistic limit coming from the thermal vorticity. So this is a very interesting term which deserves more investigation. Now, let us now go to the application of these ideas to relativistic hadron collisions. So in other words, what we have found is that we have a new term for the spin of particles, one coming from thermal vorticity and the second from a thermal shear. Now, what happens is that, of course, you have to sum the two if you want to compare with the data. And it happens that the thermal shear is remarkable. So it is mostly less than 1. Therefore, this means that the linear response theory is adequate. But on the other hand, it does contribute because it is even larger than the thermal vorticity. So this is an histogram showing the magnitude of the thermal vorticity and the magnitude of the thermal shear. So they both contribute. Now, let me just remind you what were the puzzles. So the polarization. So the idea is that, okay, the idea, of course, that arises is that, okay, is this able to accommodate this, to solve the discrepancy, you know? And now with we then set out to do new calculations of involving this new term. These are based on the hydrodynamic code by VHLLA by Yuri Karpenko, which was tuned to reproduce gold momentum spectral Richthof energy, but we obtain a similar output with another code, EcoQGP, by Gabriele Inghirami. So this, in this plot, you see that the color contour plot of the prediction of the polarization along the beam and along the angular momentum direction for the thermal vorticity term, and you see that this is negative, and this is a sign of, as I told you, that if it is negative, this means that it is in disagreement with the data. So the blue here in the first quadrant means disagreement with the data. Now, if we calculate now with the new term alone, what we found, and this is also in agreement with calculation made by the other group in which Yin was involved, we find that it is positive. So this is in agreement with the data. It has a right pattern, and the magnitude is similar. So it's on the order of percent prediction. That is encouraging. Moreover, the behavior as a function of the azimuthal angle of the component along J is also in agreement with the data. So this is very promising. However, when we sum the two, because they both contribute, what we observed is that this is almost uniform, and this is not sufficient, unfortunately. So this is a bit lower, and it is not sufficient to change, to flip the sign of the polarization along the longitudinal direction. But now comes the last idea. Last idea is the following. Have we really made the best approximation possible in these calculations? And the answer is, after all, we could have done better. Because when we analyze the data at very, very high energy, what we expect, and this is quite, I would say, I mean, I don't know if it has been, tested, but I think it's quite obvious, it is such a natural assumption that the hypersurface of hadronization is T equal constant. So because if I go to very, very high energy, the biochemical potential, that does not really play a major role, because the system is getting more and more C neutral. Therefore, the only possible thermodynamic equation which say the thermodynamic condition of hadronization can only be T equal constant. So assume then the hadronization hypersurface is T equal constant. Does this have an impact on this calculation? And the answer is yes, it has. Now, both these terms involve the gradient of temperatures, because beta is equal 1 over T u mu. So when you plug them in the phenomenological calculation, you have the effect of the thermal gradients. And this is also shown in this plot, which was made by Yuri in 2019, showing the separate contribution of the gradient of temperature, of the acceleration, and the vorticity. So separating the several sources of contributing terms to the polarization. So they do contribute. Is it a good approximation? Well, this is in general, you know, when I going back to the theory, you see, when I told you about, you know, this Taylor expansion, what I did is I Taylor expanded beta, assuming that there is a separation of scale, of course, between the microscopic and the macroscopic. But could I have done something different? Yes, because if the hadronization hypersurface is T equal constant, then what you can do, you can simply take advantage of the fact that in this integral here, T is constant, can be taken out from the integral. So beta, after all, is 1 over TU. Therefore, if T is constant, this is simply a factor which can be taken out, and you can then expand U instead of expanding beta altogether. And this is different. So this was one of the most delicate point of our say argument, which was somehow questioned by several people. But this is a very delicate and it's a subtle point that is very important for the final outcome. So if T is constant, then you can expand U and eventually find something which is different. So a formula in which T is a factor which is outside, and spin as in this under this particular condition of say isothermal hadronizations hypersurface, something which is driven only by the antisymmetric and the symmetric derivatives of the U, what is called kinematic vorticity and kinematic shear in a sense. And if you now use this formula, okay. If you now let me anticipate. If you now use this formula, then I go back to the further explanation. If you now use the formula, what you find is that indeed you recover agreement. Okay, applying the new formula, you get a different outcome. The different outcome shown here. So this is the polarization along the angular momentum. Sorry, the beam direction, which is now positive in the first quadrant, as it should be, and this is the polarization along the angular momentum, which shows that it has a maximum along the reaction plane as observed in the data. So this is the more detailed comparison between the data and the prediction. The solid line is the main prediction at T equal 150 MeV. So it is quite sensitive with respect to the final so to the decoupling temperature, to the hadronization or freeze-out temperature, as you wish. And remarkably, for the longitudinal polarization, it also yields an agreement between the data and the model, and is also very sensitive to the hadronization temperature. So a change of a few tens of MeV implies say a rise, very remarkable rise, increase on the amplitude of the oscillations, as well as in the sign if the temperature is decreased to 133 MeV, as you see. Okay. Now, here in red and green, you can see the different contributions, the two different contributions. Okay, so now let me go ahead. I would like to have a very short mention of another suggestion, of another proposal we made last year, which is still under the examination of referees, about the polarization and so the use of spin to highlight the local parity violation in QCD, which is one of the which is the main goal of finding, you know, the paramagnetic effect. Now, this is just a short introduction. This is very, I mean, I only have 4 slides, so it is very quick. This is a very short reminder of what is about. So peripheral collision in on the average, peripheral collision in heavy ion physics is a system which is invariant by reflection. Okay, so if you collide 2 nuclei with momenta which is opposite, this system is invariant by parity. However, there might be event by event, so-called local parity violation breaking due to non-perturbative QCD topological transitions induced by high temperature. This is the long-sought phenomenon with the paramagnetic effect. So if this happens, in the system, there can be produced an axial imbalance, so a chiral different population of left-handed and right-handed massless particles. And this gives rise to, in statistical, say, mechanics, this drives to an axial chemical potential, which has been used by many, familiar to many people, many of you, and which is the coefficient steering the current magnetic effect. So J, the current, electric current, proportional to the magnetic field through this axial chemical potential. So local parity violation has become then a synonym of current magnetic effect because it has been sought by this effect. Now, we propose to use the spin as an alternative method, complementary method, to highlight the local parity violation. The idea is the following. If on one event you have, say, axial chemical potential, then this implies, and local equilibrium is achieved, then this means that you have an extra term appearing in the local equilibrium density operator, which involves the product of the axial chemical potential normalized by temperature times the axial current. Then after some calculation using linear response theory, what you can do is that you can find that there is another contribution to the spin polarization vector, which is proportional to this axial chemical potential. Okay, in a form that eventually it is a change in the helicity. So it's a term contributing to the helicity of the projection of the spin onto the momentum of the particles. Sorry, let me go back. Now it is important to say something, which is why haven't we seen this? The problem is that this zeta A changes of sign on event by event fluctuates because this topological transition is induced by, it's a stochastic phenomenon. Therefore, this changes, and then you measure over many events. If you average the spin over many events, you won't be able to see it. But what you can do, you can see it in the analysis of if you correlate particles at large angles. So this is a suggestion. So if you have this can be done in a completely model independent way. So regardless of this formula. So if you have axial chemical potential, so you have an increase of increased chance of producing right-handed hyperons, for instance, over the entire, say, azimuthal plane. What you can study is the correlation between particles at large angle, because if parity is not violated, what must happen is that on the average, if you have, say, positive helicity in the say first two quadrants, then you must have negative helicity in the lower two quadrants. So there is a reflection symmetry of the helicity by the reaction plane. Whereas if you have local parity violation, there isn't, and you might have this kind of situation which is fluctuating event by event. So once it's positive, once it's negative, and after it is averaged away. But studying the correlation, so the correlation between the particles at large angles, say at pi difference, for instance, this phenomenon can be found, because the correlation between the helicity correlation between the particle going up and down is opposite, and it can be measured event by event with respect to the parity conserving case. So by plotting the helicity correlation function as a function of the azimuth, one can really determine whether there is an axial chemical potential, say, affecting the final hyperons in this respect, and so a finite integral of this helicity correlation function. And this is our suggestion. So I think I'm done. I hope that I was saying within the 50 minutes. And let me summarize what I have shown. Let me make a point that I'm very fond of. As a first point, quantum statistical mechanics is an essential tool to properly deal with spin physics in relativistic fluids. It was just thanks to this formalism of statistical operators, and that we could find something. Local thermodynamic equilibrium showed an unexpected term relating spin polarization with a symmetric gradient of Ford temperature, which was independently found in a very similar study. So this is good, bears out this finding, and this is still under further investigation. Local polarization puzzles can be solved. I mean, those at least those observed so far can be solved by including this term in the numerical analysis with an extra assumption, so that hadronization, which is quite natural, the hadronization takes place at constant temperature. So in other words, in this the Taylor expansion of the hydrodynamic fields may depend on the hadronization conditions. So it's not really a rigid expansion. So it might be, the best approximation can be different according to the situation that you that is expected to be in the particular fluid you are dealing with. Important. This has a, I mean, if this is confirmed, I think that this has important phenomenological consequences, namely, the local equilibrium picture, so the ideal fluid picture seems to hold in the spin sector too, and not just the momentum for spectra of particles. And also it seems to be sensitive to the hadronization temperature. So if you believe this, then spin can be used as really a nice probe of plasma formation and decay, because it is sensitive to the gradients. Therefore, this makes it really a very sensitive probe of the hadronization conditions. And then finally, I advertised this work where we suggested the spin can be used and is an independent probe of detecting the local parity violation in heavy ion collisions. Thank you very much for the attention.
Well, thank you very much for a nice talk. And now we will go to questions. So first question is Rajiv Singh.
Hi, thank you very much for the nice overview. Just one clarification that you took out the temperature, the T factor out of the integration, just on the assumption that the hypersurface is defined as at constant temperature, right?
Yes.
Okay.
You mean?
Yeah, where you means Taylor expand U, not beta. Yeah. This one, yes.
Here.
So
Yes.
just on the assumption that the hypersurface is defined at the constant temperature, therefore you took out the temperature out of the integration.
Yes.
Right? Okay.
Yes.
Okay.
You can do this only, of course, you can do this only if sigma FO is T equal constant. Otherwise, you can't do that. Sure.
So
if you have a
okay. Yeah. Please continue.
Yeah. If for instance, if you go to low energy, you expect that the hadronization hypersurface is not T equal constant, because it will be, it would be a hypersurface where both T and mu B vary, because mu B is significant. And therefore, you cannot do this.
Yeah.
Okay. So this is specific for very high energy, where the mu B is essentially zero everywhere.
Okay. Thank you.
Now this is you gave me the opportunity. You gave me the opportunity to make a very simple illustration of this, if you wish, because this has been many people ask me about this. How can you do this? But then you should get the same result. So if you wish, I can illustrate this with a simple example.
Yeah, please.
But if there are other questions, then I maybe somebody.
There are more questions, but if it doesn't take long, please show.
Yeah. Okay. So that is in order to understand the point that was criticized, not criticized, but I mean it was questioned by several people that I had the chance to talk to. Let me make a very simple example of function of two variables. So assume you had to make this calculation. You want to calculate some integral of a function of two variables in a Cartesian plane with which is weighted by the exponent of square root of x squared plus x squared. And then you have to do this integral over a line. So instead of integrating in space-time and then I integrate over say, a manifold of dimension 3 embedded in Minkowski space-time, now I integrate over a line over the Cartesian plane. And this line is a circle. So assume that the line is a circle. It means that s squared plus y squared is constant over this line, right? Now also assume that g, which is what happens when we calculate correlation functions in this formula, is g is a very peaked function around some point, line on the circle. So for instance, Gaussian, with very narrow Gaussian. Now, then what you can do is that by using the techniques that have been learned at the university courses, that I can expand, Taylor expand the exponent around this point, okay? And then write something like this. So because this is a very peaked function, therefore the other function, which is relatively smooth, then I can expand in Taylor series and retain just the value which is in x naught, y naught. This is quite clear. I mean, if it was a delta, for instance, you would have only one value, right? Now, if you expand this, what happens is that eventually you get e to the r, which is the radius of the circle, times the gradient. The gradient of r, which is pointing outward, which is multiplied by x minus x naught times gxy integrating ds. But this is clearly stupid, let me say, because since gamma is a circle, what you can do is that you just can take this out, because x squared plus y squared is constant over this line. So why should I expand it if it is constant? And then eventually you have to compare this, which is the exact formula. This is exact, because gamma is a circle, with this, which is the approximation, and the approximation is bad. It differs by the fact that now you have a spurious function in the integration. So the same thing happens. This is just an analogy to show that if you say expand blindly, functions in the integral, what you can obtain is a worse approximation. Okay. This is now to illustrate. This is a point to illustrate why it is convenient to take out temperature if you can, and not to expand it in Taylor series in the integrand function.
Okay.
Just a small follow-up question, a small clarification. If I say that if I say that the hypersurface is defying a constant temperature, it means that each point on the hypersurface have the same temperature, correct?
Yes. Each point on the surface has the same temperature, and therefore the gradient of T is perpendicular to the hypersurface.
Okay, thank you.
Does not vanish.
Yeah.
The gradient of temperature does not vanish. It is perpendicular to the hypersurface.
Okay.
Okay, let's go to the next question. I think we already spent quite a bit of time on that. Carl Weinsteiner has the next question.
Okay, hi. Oh, I don't know if you can see me.
Yes, we can.
Okay, I cannot see myself. So. Okay, thanks for this talk. This is really very, very interesting. I have.
Sorry, Carl. Can you increase the volume of the microphone?
Volume. Oh, I see. Sorry.
Actually, I can hear him really well.
Unfortunately,
is it better now?
Sorry?
Is it better now?
Yes, it is. Yes, definitely. Yeah.
Okay. I can crank up my microphone. Okay. Yeah. So I have two sort of related questions. The first is, in your treatment, it's not clear to me, is this still hydrodynamics, or is this something which goes beyond hydrodynamics? For example, you had this object, this q mu nu object, which isn't really a tensor. And so this is something which usually in hydrodynamics, say, if we just think of, hydrodynamics in terms of the fluid velocity and temperature, and so we don't have that, right? We only have an energy momentum tensor plus constitutive relations. Related to that is that there are ambiguities at the derivative level of what we mean by fluid velocity, right? So there are frame choices and so on. And there didn't seem to be any of these ambiguities in this formalism. So I was wondering if this is hydrodynamic, or if this something is something beyond hydrodynamics.
This is a very interesting question, of course. And it depends on, I think it partly depends on how do you define hydrodynamics, of course. What I can say in general, so maybe I don't have a very good answer to your question, but what in general these what we were dealing with are quantum corrections, because spin is quantum, and quantum corrections in other contexts, for instance, they really somehow question our interpretation of hydrodynamics. Therefore, I believe that this is a, I mean, your question is very interesting, but I cannot tell you really yes or no.
Because you see, usually we think of doing a hydrodynamic evolution from an initial surface, right, as to some freeze-out surface. And then, but in this hydrodynamic evolution, we would lose all non-hydrodynamic information, right? All non-hydrodynamic degrees of freedom, which might be there initially, they would all decay very fast. And at the end, we think we can describe everything by an energy momentum distribution and nothing more, and the temperature and the fluid velocity. And so, but here there seem to be more objects than what could give you a hydrodynamic.
No, I mean, that is, if you look at this formula here, it does not really contain, for instance, it does not really have any special, say, dynamic coupling or anything else than, say, hydrodynamic fields, right? So because you have momentum, and then you have this tensor side. So therefore, however, I mean, the meaning, this term has been found, say, this year, I would say, by not just by me, but by another group, and therefore, its understanding is still still in progress. So I don't know whether this is somehow leftover of non-hydrodynamic, say, mode, or this is just say quantum correction to the hydrodynamics, which is my interpretation.
I probably shall I understand it of a sort of matching condition. I do the hydrodynamic evolution, and at the end, I use the information from hydrodynamics to match it to this spin distribution of the hadrons. So.
No, we don't match anything in a sense. So sorry, we match. So we match the energy density. So in other words, if you look at, so if I can say summarize how this was obtained, is that so everything is within this operator. This operator has been obtained by using matching of the momentum and the energy density, not of the spin. And possibly if there is some conserved current. So what you say, in fact, maybe okay. So this operator is obtained. This was in the original papers, by maximizing the entropy, by constraining. So the system, this is a matching condition, constraining the system to have the given energy density, given momentum density, and possibly the given charge density. So there is no condition on the spin. So in other words, these formulae are consequences. So there is they are derivations, though they are not, they do not contain any matching. But as spin degrees of freedom is concerned. Actually, in the formula, in the spin tensor approach by Florkovsky and Rajiv Singh and others, that they have been working on that, there is a matching condition on the spin, indeed. But this is just specifically designed. In this case, we don't have. So this is just say the minimal, say the minimal set of assumptions in a sense.
Okay, thank you. I think that's
Okay.
I
Okay,
hope that I have
go.
answered to some extent, although I mean this is
yeah, I understand it's still under investigation, but it's a very interesting question, I think. Thank you.
Yeah, it is. Yes, absolutely. Yes.
Okay, let's go to the next question then. Graziano Mileto. I don't think there is a second question. Where do you see the second question?
Beyond polarization, do you expect to have quantum correlations in the QGP state, such as entanglement?
Yeah.
Well, I mean, that is this is a major question. I don't know. I mean, I cannot. Quantum correlations. I mean, of course, there can be, of course, but in this approach, I think if you maximize the entropy, then most of the quantum correlations are washed out. So
I guess it is an open question that has to be looked into, but
yes,
probably it's not a lot of the effect. I do have a very simple question before we wrap this up, though. The question is as follows. When you are considering this other freeze-out model, when there is a fixed thermal temperature, basically it's something that in some particle dynamics models, they actually do all the time. So my question is natural, do they reproduce the corresponding spin correlations or not? That would answer your model question.
Let me say rephrase your question to make sure that I have understood correctly. So your point is that assume that you have a model where freeze out is dynamic. Is it your point?
Well,
So
in the dynamic particle models where you simulate basically particles, you could actually enforce freeze out at fixed temperature. Basically, that's what they really do at high energies. And then they should reproduce all the polarization observables exactly, or correctly, I should probably say. Do they? Do you know?
This has not been done so far. This has not been done so far, as far as I know. What I know is that it is a formidable task to implement, to trace polarization in a collisional model. That what in this in chiral so if you want to simulate colliding particles, what in most models like URQMD, for instance, they follow the momentum, right? So they have position and momentum. There are collisions under some conditions, and they assign a momentum to each particle. If you want to do the same for the polarization states, this is really very, very much harder. And so there are no codes able to do this. So you can only make calculations on the average, statistical averages. And therefore, I don't know if this was your what you were thinking of. I think that is this will take a long time, because the spin, in other words, following or tracing the changes of spin polarization, spin states in collisions of particles is extremely difficult. And also I mean that most of the cross sections are unknown. Therefore, it requires a lot of model building, work.
Okay. Sounds fair. Okay, I don't see any other questions. So using this opportunity, I would like to thank Francesco again for a nice presentation. And with that, we will